Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, Benefits of Intelligent Drawing Practices. Our speaker is Matthew Leos. Matt Leos has over 4 years of experience in process safety management related to project execution in the oil and gas industry. He served as the line of service lead for the computer-aided drafting department at Provenance Consulting. His expertise is in process safety information data management, software development and implementation, and computer-aided drafting. He holds a BS in mechanical engineering from the University of Texas and is an engineer in training within the state of Texas. One quick note before I turn this session over to Matt. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Matt Leos. Hi, Matt.
Hi, Pam. Thank you for that introduction. Good afternoon, everybody. Thanks, Pam, for getting all this set up, and thanks to AICHE for this opportunity. So in this presentation, I'm going to be demonstrating the benefits of setting up your facility CAD drawings in such a way that allows for information stored within those drawings to be used to greatly reduce the time to perform engineering evaluations. So first I'm going to outline the main benefits of using intelligent drawing practices. We'll go through the different drawing types and data types that I'll be discussing, examine different levels of intelligent drawing practices. We'll go through some example situations. We'll talk about what your steps might be after this presentation, and then we'll wrap everything up. So before we begin, how many times have you been part of an incident investigation that uncovered an issue in your facility and you had trouble quickly quantifying the problem? Or have you ever been part of a project where the information you needed was on your P&IDs and you had to open up a big set of your drawings one by one to find the data? Or how many times have you performed a data validation effort on your drawings, but there were so many items to correct that you never got around to updating them? So my intended audience for this presentation are those that can relate to the questions I just proposed and any situations that might be similar. Engineers at a refinery or plant who currently don't utilize the data inherent into CAD drawings will really benefit from this presentation. And you don't need any CAD background or drafting, and actually this presentation is not intended for drafters, but really for different refinery groups such as engineering and maintenance, environmental operations, and safety. So the three main benefits I'm going to talk about are allowing your engineering evaluations to be performed faster and cheaper, allowing tracking and reporting from facility drawings that would not otherwise be possible, and ensuring data is more consistent across your drawings and your systems. So I keep saying intelligent drawing practices, and what do I really mean? Well, first, I want to say I don't necessarily mean advanced CAD software. I think when people hear smart drawings or intelligent drawings, they may think of some advanced facility, like plant suite of software, or at least an external database that might be attached to their CAD drawings, and then that database can import and export data to and from the drawings. While those definitely are examples of intelligent drawing practices, that's not exactly all I'm talking about. So I really mean just ensuring your drawings are data-driven. So ensuring that you're able to extract or pull information off of your electronic drawings and use that information for other engineering evaluations. So again, I keep saying drawings, and what drawings am I talking about? Well, in this presentation, I'm really concentrated on facility, refinery, petrochemical facility drawings. So for example, P&IDs, PFDs, plot plans, ISOs. And historically, these drawings are mainly used as printed schematics to visually represent the facility. So you might print out a stack of drawings and go to your PHA to walk through them, or you might print out a single P&ID and redline it for an MOC. But really, we're going to be discussing the data inherent into the CAD drawings themselves, the electronic files that can be exported and used externally. So I keep saying data, and what data am I talking about? Well, I'm going to go through a P&ID as an example, and while I go through this P&ID, try to think of other document types that we discussed earlier, such as plot plans and PFDs and ISOs. So on this P&ID, you have your equipment information, and I'm not just talking about the spec blocks up at the top, but also if you just look at the outline of your equipment, it tells you a whole other set of data, right? This vessel, I can tell, is a vertical vessel. There's 2 heads. You can see all the trim, all the connections on it. And the pump, you can see, is a horizontal centrifugal pump. And then also you have the tag numbers associated with those. You also have your instrument information, including instrument type and loop number at the least. You may also have, some alarm information on your drawings. You have valve and PSV information, and not just the size, but also the type of valve by looking at the symbol. You can maybe see if it's normally closed, if it's car sealed, if it's flanged, based on if there's flanges on the valve, if it's a control valve of some sort, or if it is a PSV, and then the PSV information associated with that. And finally, you have your piping information and your line specification. So you can tell, the size of the pipe, the process, the rating, the material. You may be able to tell if it's insulated or not, and any changes in that pipe, such as, above ground, underground breaks, or metallurgy changes. And then just by looking at the flags going into and out of the drawing, you can tell, where the process is going to or coming from. So there's all this data on your drawings. And so to reiterate, intelligent drawing practices simply means making sure that all of this data is able to be used not just in the printed schematic version, but also externally, to be able to take the information off of the drawing, off of the electronic files, and use for other engineering evaluations. So real quick, I want to go through how the data is actually stored on these drawings. And so some of these terms I use may be associated with certain software. The concepts are going to be similar throughout all of your CAD software. I'm going to be using terms like blocks, attributes, and properties. So a block is a collection of objects within your drawing, including lines, text, attributes, that form one single object, right? So in this case, you have your PSV block. You can see you have the data associated with that PSV, the PSV tag, and then the actual symbol of the valve. And all of those are associated together. Then you have attributes. So attributes are data values assigned within that block. You can have, in this example, the inlet size, orifice, outlet size. All of this information is associated together, again, with the block. And now, as an attribute, it can be pulled individually and then used externally. And then finally, we have properties. So properties might be metadata associated with different object types within your electronic drawing. So each object might have a different set of properties. But some examples might be the name of that object, or the color, or the layer, or the line type, position, font. So all these are different properties associated within an object. And so all of this data It can also be pulled, right, and exported and used in some sort of evaluation. So we've gone through the different drawing types. We've gone through how data is stored. So now I want to go through different levels of intelligence, right? So you may be wondering where your facility falls. Does your facility have intelligent drawings or does it not? And it's really a scale, right? So as I go through this, try to identify where your facility is so that we can discuss later where you might want to take it. So first I'm just going to say no intelligence would be if your drawing wasn't even in a CAD software, right? There's no other data inherent to your drawings because it's not an electronic file. But once you get out of that region, you get into what I call basic intelligence, which is basically using blocks and attributes within a drawing. So the lowest level is actually if you just have your drawing in a CAD software and you don't use any of the attributes or blocks. So you just have basic lines and free text. That would be what I would consider the lowest level of basic intelligence. Then next we have some data integration and inconsistent CAD standards throughout your facility. But then you can add consistency, right? And anytime you add consistency, you're going to gain some sort of ability to do something to be able to pull a certain set of information from your drawings. And then the highest level of basic intelligence would be if your data is all defined as blocks and attributes, kind of how we showed earlier. And then the next set, I have advanced intelligence. And so this would be generally if you have a dynamic external database associated with your drawings. Right, so I kind of split these up because this may take a different set of CAD software. You can have an external database associated with your drawings where all of your information is actually stored and your drawings just reference that database. That database can also be linked to other engineering software. So your P&IDs, for example, may be linked to your relief systems software. And then finally, I would consider the most type of intelligent drawing would be, a complete 3D facility model where all of your disciplines are within one drawing. A design firm might use this type of drawing software more, because now you can combine your piping with your support and everything and make sure that all of your disciplines are consistent. So most of the facilities that I've worked with fall within this kind of middle basic intelligence region, where you have consistent CAD standards and some data integration, but it may be inconsistent across your entire facility. And if your facility is in there, then I would recommend at least improving your intelligence to this level, where you have your complete user-defined data integration. So all of your symbols are blocks and attributes. And we'll discuss this a little bit later, but comparing what it takes to get to this level as opposed to the advanced level, there are certain benefits of the advanced intelligence, but we're going to see that just by having basic intelligence that you're still going to save a lot of time and effort. So in order to demonstrate this, I want to go through some examples. So let's go through 3 example scenarios, and we'll use 3 example facilities. I call Plant A, Plant B, and Plant C. And then in each scenario, we'll have a baseline case. And so each facility has different levels of intelligent drawings. Plant A has the external database. Plant B has the complete user-defined data integration, so all blocks and all attributes. And then Plant C has some data integration, but maybe inconsistent CAD standards. So let's go through 3 scenarios and see how each facility handles that scenario. So scenario 1. During quarterly inspection, operations car seal list was found to be inadequate. So you need to locate all of your car seals missing from the car seal list so that they can be added and properly tracked. So that's the scenario, and then as we go through these examples, I'm going to have some time estimates, and so I want to give a basis for those estimates. So in this case, let's assume we have 400 car seals identified on 150 out of 300 P&IDs, and there are 25 car seals need to be added to the P&IDs. So that's just the basis for some future time estimates. If you don't know what a car seal is, kind of think of maybe a zip tie that you can attach to a valve handle and make someone think twice about turning that valve. So what steps would you use for this scenario? Well, first you'll have to figure out, well, how do I find these missing car seals? And you might identify the P&IDs to be a good place to start. And then on your P&IDs, so you'll actually have to locate each of the car seals and then compare what you find on the P&IDs to the operations car seal list, walk down the discrepancies, and then update both sources. So we're going to look at 3 of those steps and see how using intelligent drawing practices can improve those steps to actually decrease the time it takes. So in this section, and this is how each scenario will look, well, I'll have the steps on the left, the task in the middle for the facility or for the baseline, and then on the right, have an estimate on the hours. So for this baseline case, you know, it's a manual effort, right? You have to print out your stack of P&IDs, go through one by one, identify where each of your car seals are, and then compare whatever you find on your P&IDs, again, manually to your operations list. And then after you do your walk down and your discrepancy checking, you'll eventually have to update each of your P&IDs. So those might be the general steps you might take, and on the right I have some time estimates for those. This is what a P&ID might look like. This is a very, very simplified version. Usually P&IDs are, you know, a little bit more busy. But you'd have to identify all the CSO and CSC, right? So it might take some time looking around the drawings, and you might miss some. Here's that zoomed in a little bit more, the CSO and CSC. That's how you identify a car seal on a drawing, on a P&ID, for example. So the baseline case compared to Plant C, even with their minimal intelligent drawing practices, they can still get some time savings over the baseline case if they perform a text extraction on all the text on all of their drawings, right? So you can do a facility-wide P&ID extraction for text and just look for CSO and CSC. That'll tell you which drawings at least have car seals. So that at least eliminates all of the drawings that don't have any car seals on it. You don't even need to look at those. So again, Plant C, with their limited drawing standards, their limited data integration, is able to shave off, you know, half the time it takes for that first step. The next 2 steps will be the same, right? You'll still need to compare your P&IDs with your operations list, and you'll still need to update your drawings. Plant B, however, is able to do a very similar extraction. So now you can think of looking at all your valve blocks on your drawings and looking within those at the CSO and CSC attribute. So here I have an example of what an extraction might look like. Right, so on the left, you can see the table on the bottom that we have the name of the block. Kind of in the middle to the left, you have the attributes associated with that block. So in this example, we have size, position, and then an attribute called ID number. And on the right, I just pulled some of the properties of that object in that drawing. So generally, when you're doing these extractions from your drawings, you can pick and choose which attributes or properties you want to see. And then obviously, with an external database, you can see everything, and then you maybe write some sort of query to pull exactly what you want. From this, you can identify which have car seals by looking at the position attribute and looking for CSO and CSC. So the second, or the middle step on this slide, I actually have an increased time estimate, because what I want to do now is I have that ID number attribute in my valve block. I want to use that for my car seal numbers so that in the future, you can just compare your operations car seal list straight to your P&ID ID number attribute. Right, so now it's like a one-to-one comparison. You're just looking for that ID number instead of having to open up each P&ID and try to figure out, okay, well, this is the inlet car seal on this PSV, for example. And then the final step is still the same, to open the drawings and update. So again, I just want to reiterate that this is a one-time effort to go through and to add the car seal numbers to the ID number attribute. This is what that might look like, right? So you might just put whatever ID number is associated with that car seal right in that field so that you can compare that to your operations list. Now, Plant A, this is a very quick effort for Plant A because they can actually do that comparison of the ID number. So we'll assume Plant A, with all their intelligence, has gone ahead and already placed the car seal number in that ID number attribute, and maybe in their intelligent drawings they actually have more attributes. Generally, you can set up however many you want, make your data however granular you want. So we'll go ahead and assume that they can just do that comparison straight in a spreadsheet and never even have to open a P&ID, right? So they can just compare that car seal number on their drawings to the operations list and see the discrepancies. Eventually, they'll have to open up the drawings and make the updates as well. So just looking at all the time, let's see where we are able to make some savings. So straight off, we saw that by doing the text extraction and just looking for CSO and CSC, that eliminates all the drawings that don't even have that as a possibility. We're able to save a lot of time by comparing the ID number on your valves to the car seal list without opening the drawings. And that's actually what Plant A was able to do and what Plant B will be able to do in the future. Let's go ahead and look at scenario 2. An incident investigation found relief device data to be discrepant between the P&IDs and relief systems management software. The relief system software was deemed correct, and the P&IDs need to be updated. So the basis for my time estimates here will be 1,000 P&IDs and 1,000 relief devices. And then of those 1,000 relief devices, we have 200 discrepancies. So how would you handle the situation? Well, I think it's pretty straightforward. I think you just need to identify the data on the P&IDs, identify that same data in the software, in the relief device software, compare them, and then update the drawings. And so now let's key in on these 3 tasks. So the baseline case, again, very manual effort, right? You need to go through drawings one by one in order to find the release device data, and then compare that data, again, one by one, by hand, with the release device software. The time estimate on the right shows this is a pretty big effort. Here's that same P&ID, and this is what you'd have to be looking for, right? You'd have to look for all the PSVs and try to find all the release device data. Again, you might be able to miss a couple if you're just doing this, manually. So the baseline compared with C is actually the same. Plant C does not have the blocks, the attributes within that PSV symbol in order to do anything intelligent with, right? So you still have to go one by one. You still have to do the comparison by hand, and the time is still the same. However, plant B, now we see where it gets pretty quick, because with plant B, they are able to do an extraction of the data from the P&IDs, look at the PSV information, and then now in some sort of spreadsheet, now maybe Excel, they can do some sort of comparison or some other software that compares data and see where the discrepancies are and see where the P&IDs need to be updated. So here I have an example of what that might look like. Again, on the left of this extraction, you see the name of the block. In the middle, we have all the attributes associated with it. And on the far right, I just pulled one of the properties associated with that block, and that's the file name that it's on. The last step, still the same, to update the drawing. Now again, plant A, now this is even faster, right? I'm going to actually say this is not even an issue with plant A, because we're going to assume that they were able to link that database with their release systems database. And so now you can imagine if they're linked in some way where you make one update to the release systems database and that update is automatically made to the P&IDs, you would never get out of sync. Now, this is a pretty ideal situation, but you can imagine with this internal database that it is definitely a possibility and definitely doable, especially within some of those advanced CAD software and their suites of software. So now if we look at this information altogether, you can see that we save a ton of time by being able to extract all the information off the drawings and not having to go drawing by drawing, one by one, looking for the PSV data. And we can save even more time when we're able to do that comparison between the P&ID information and the release systems database information via some spreadsheet or some other software. And then finally, you're able to save all of the time by having your databases linked, right? By taking advantage of the most advanced type of intelligence where your database is actually linked to an external database. Now I want to go through scenario 3, which deals with small bore threaded piping. And we're going to define that as diameters up to and including 2 inches, which may or may not be how your facility defines small bore threaded piping, but that's how we're going to do it here. And so that small bore threaded piping is actually more prone to leaks and failures from corrosion and vibration. It needs to be evaluated at your facility. So identify how much piping you're going to need to evaluate and prioritize that based on the risk. So the basis here, we're going to use isometrics. So we'll say 2,000 out of 3,000 of your facility isometrics have piping that's 2,000, or sorry, have piping that's 2 inches or less, and the same for your equipment inspection drawing. So what steps would you go through for this scenario? Well, what I would identify would be to look at all of the connections, all of your threaded connections on your ISOs. Look at all of your threaded connections on your equipment drawings that are all 2 inches or less, and use that information, and then prioritize those drawings based on the pipe class within each of those drawings. So generally, in an isometric, you'll have a single pipe class for that entire drawing. So for the baseline, again, very manual effort, go through isometrics one by one and just look for 2-inch threaded connections. So you'll do this with your isometrics, and also do this with your equipment drawings. And then you can prioritize those based on the pipe class of that drawing. So I have actually 200 hours estimated for this effort. And so this actually may not be a feasible option for you, because really taking 200 hours to go through this list, it may be worth it to find some alternate means of this data. Because what you're going to have to do is go through each isometric, look for this information, see if it's a threaded connection, see if it's under 2 inches or 2 inches or less, and that's just going to take a ton of time. So comparing the baseline to C, I've actually added another step for Plant C. So Plant C is actually able to improve the time on this by doing another text extraction, right? So now you can imagine extracting all the text and just looking for anything under 2 inches or less, sorry. So what that's going to do is eliminate all the drawings that don't even have any connections 2 inches or less. What you won't be able to do is identify if they're threaded connections or not. So you'll still need to manually go through each drawing that you've identified that at least has 2-inch or less connections and see if those connections are threaded. And then again, you'll just prioritize based on the drawings that you find. And so here's an example of the threaded symbols versus the like a weld neck example. So plant C compared with plants A and B. Now I'm going to say that A and B have a similar process, and there's no actual benefit of having the external database. But you can see that this time, there's almost nothing, right? Because you're able to do quickly to pull all of the blocks off of your ISOs, and we're going to assume that this facility, or that these facilities have identified some way whether these are threaded connections or not. So in this example, we actually use the name of the block to tell if it's threaded or not, and the size, obviously, to tell if it's under 2 inches. So this might be what you might extract if you just cared about the size and the name of the block and the file name. So from here, you can eliminate everything that's not 2 inches or less. And then from there, you can identify which of those are actually threaded. So as you can see, it's a very straightforward effort just to pull that list. Now you can see all of your threaded connections, and now you can tell, at least get a good estimate, right, of where all of your all of that piping exists that you may need to evaluate. So looking at the time, we see some time savings by doing the text extraction, again, which is basically all Plan C can do in this case. And then even more savings with plants A and B that are now able to do the block extraction and look for threaded blocks 2 inches or less. So how do all of these scenarios compare? Well, just by looking at the totals at the bottom, you can see, as you would expect, right, as you gain intelligence in your drawings, the time decreases for these efforts. Right, so and actually what we'll see is, I'm going to pull up a graph, that there is a huge savings going from your baseline to plant B, and actually, so just going from plant to plant, right, we can just look, so there's about a 20% savings going from the baseline to plant C, but then to B, we have this big jump, right, and that's without changing your CAD software. That's going, keeping your basic intelligence, but making sure that all of your blocks and attributes are utilized. Plant A, of course, reduces this time almost from 400 hours that I estimate to nearly nothing. So there's huge benefit of going to Plant A because it basically reduces this 10-week effort to a day and a half. So these are just 3 scenarios that I identified. We might be able to use our intelligent drawing practices to help us, but there's clearly a lot more. You can imagine comparing your P&ID instrument loops to your loop diagrams. You can imagine comparing your emergency response equipment on your plot plans to your PM and inspection list. So now you can make sure that all of your emergency response equipment is being PM'd properly. We haven't talked about too many of the drafting benefits, but if you ever wanted to update a symbol, it's much easier to update a block than it would be to update free text or lines. You can perform some LDAR tagging very similarly to how we identified car seals. You can do a drawing standards audit by doing an extraction of all your blocks and comparing the block names that you would expect to what the extraction actually pulls, and identify where you have symbols that aren't exactly your CAD standard. And then now imagine if you're going into a PHA, imagine doing a flag check on all of your P&IDs in that unit or that facility so that you're not spending time in your PHA making sure, or I'm trying to figure out where this pipe connects on what drawing. If your flags or blocks, you can do that extraction, right, and then do all that comparison beforehand in some spreadsheet, maybe with some routine, or maybe with some built-in functionality into that CAD software. And you can imagine do the same thing for PFDs. So by now, I'm sure you're curious, okay, well, yeah, I'm sold, right? I really want this advanced, or these intelligent drawings, so now what do I do? Well, just really go talk to your drafting team, and if you're already using intelligent standards, then imagine all the time you just saved. Call your spouse, you're going on vacation, right? However, if they're not using the level of intelligence that you want, well, it's time to call your PSI manager because you may want to get your drawings updated. So what does it take to get your drawings updated? Well, I'm going to go through some steps. And really what you want to do is, first identify the opportunity you have. Right, we've looked at some P&IDs, we've looked at some isometrics and realized, okay, well, where we have some of this data. So you want to go through your drawings and realize where you have the data and realize how granular you may want to make your blocks and attributes. So that would be your next step, right? Creating all your blocks, updating your CAD standard with these new data management techniques. You'll want to identify a mapping between your old symbols and your new blocks, because the next step is to utilize hopefully some kind of built-in feature of your CAD software to make this transition. So you can imagine this may be a huge effort if you have thousands of drawings at your facility to update from your old standard to your new standard. Well, a lot of the CAD software out there have some sort of built-in conversion functionality where you may be able to kind of tell it what your old symbols are, your old blocks, and it may somehow map it to your new standard. That may require some level of intelligence already set up. However, if you have some level of consistency, even if you don't have all the blocks and attributes already identified, you may be able to develop a routine internally within your own facility, very specific to your drawings, to update your old standard to your new standard. And just to give a quick basis of this, you can assume 1,000 drawings on plant C. And just the order of magnitude we're talking about, I mean, you can imagine a couple hours per drawing to do this upgrade. So I have estimated 2.5 hours per drawing to convert to plant B, and 3.5 to convert to plant A. So it takes a little bit extra time when you're using more intelligent standards to initially set up your drawings. Plus, converting to plant A, you have the cost of your advanced CAD software. And again, we're assuming going from plant C to plant A. Plant C, we're assuming has some basic CAD software. Plant A, to have that external database, maybe you have to have some advanced CAD software. So this is order of magnitude, and it may be more or less depending on your facility. If your drawings are very complex, or if they're very simple, right, it may be a little different, but somewhere around here is maybe what you could expect. So I guess really what you have to weigh, right, is it the benefit of getting to plant A? If that, outweighs the amount of time it's going to take up front. So once you've made all your updates to your drawings, you want to train your new CAD team on your new drafting practices, right? So there may be a deviation from the way they have been doing things. And then finally, you want to inform all of your engineers on the new capabilities of these drawings. So real quick, I just want to throw up some quick advantages of the advanced versus the basic. You may be kind of wondering, well, I'm at plant C, do I need to get to plant A, do I want to get to plant B? So with the advanced intelligence, generally there's just more information on your drawings. For example, the ability to embed process data into the piping may be a feature for the advanced intelligence, but maybe not on the basic level. So if you had a 2-inch pipe and there was an attribute 2 inches associated with that pipe, the ability to insert a block, a valve, for example, and have that valve automatically pull that information from that line. Those types of functionality generally tend to be on more of the advanced CAD software. Ease of data access. So you can imagine with your external database, an engineer may be able to pull the information much easier than if that data was still stored within the drawings and then having to do some sort of extraction or having your drafting team do an extraction, or maybe even just not even having the CAD software might be a limitation for your engineers. So with this database, they can get to the data much easier. And there's an added CAD software functionality generally when you have this advanced features, kind of like the example I gave earlier. So I think by now we've identified that using intelligent drawing practices, you can drastically decrease the time it takes to do a lot of your projects in your facility, right? So just the time it took plant A was generally much quicker than it took plant C to perform any of these tasks. using these intelligent drawing practices allows tracking and reporting from facility drawings that would not otherwise be possible, right? So Plant C was not able to put the car seal number within their CAD drawings, so they're not able to track their car seal numbers within their drawings. So any comparison of their P&IDs to their operations list is very difficult in a manual effort, really. And then finally, being able to ensure data is more consistent across your drawings and systems. We can remember Plant A when they had their data directly linked to their release systems database, that data was consistent but between the two systems, and now you have confidence in your data that your P&ID information is the same as your release systems information. So thank you all for your time, and I think now we can open it up to some questions.
Thank you, Matt. Your first question, implementation for a greenfield facility is pretty straightforward. What are the hurdles, costs for a brownfield?
That's actually a good question that I haven't actually thought about. We'll start it off. I'm gonna start. I guess we'll keep track of these questions. Pamela, is there a way I can get back to this person?
Yes, Matt. I can forward you his email, and if you need to get back to him later, you can do that.
Okay.
Okay.
Right,
same person asked another question. Okay. And the same person's second question was, another hurdle is implementation cost at your engineering contractor, whom could have either no intelligence or a different non-compatible software. What strategies do you suggest or have seen used?
So the question is, what strategies when your contractors have different software than you have? Is that the question?
Let's see, right, when they have different non-compatible software, yep.
Right, and so we see this pretty often, right? Especially with maybe your design contractors where they have the really advanced CAD software and you maybe have a more basic functionality. And so generally what I've seen is that, it's actually pretty difficult to merge those two, to marry those two systems. What I would recommend is, getting your drawings, so your facility drawings, at a place where you feel comfortable with that level of intelligence. If you wanted to, you could set up some routines in order to map their systems with yours. I think it's really dependent upon maybe the size of the project that contractor is working on, because you can imagine, if it's a really big project and you want to pull all that data into your drawings, if your drawings are set up even with your basic CAD standards, or sorry, your basic level of intelligence, and you have your blocks and your attributes, you can actually map, right, the data on those other drawings into yours. So you may not have to have exactly compatible drawing types, but if you can get the data in some sort of spreadsheet or some sort of way that can be imported into your drawings, maybe you don't need the exact same software.
Okay, thank you. Do I need to have more experienced drafters if using intelligent practices?
And so I don't think you need a different level of drafter using advanced intelligence versus basic intelligence. I think it just comes down to, making sure that everyone is on the same page for, what level of data do you want to store in your drawings? How do you want to manage that data? And I think, lining out some basic procedures and standards, you can easily, inform your CAD team that's been doing maybe a little less data management, more of just schematic type drawing. But with some basic procedures, I think, there's not a problem there.
Okay, thank you. Are there any pros and cons for the drafting team in using intelligent practices?
Yeah, so we didn't talk about this too much. Generally, it's a little, well, it could be quicker using more intelligent standards. The example I gave, if you have a line, a pipe that's 2 inches, for example, and you wanted to insert a valve on top of that, then you could map that data straight from the pipe to the valve, and your drafting team never has to type anything, right? It's automatic. There's a lot of automatic functionality when you start having a lot more data at your fingertips. So it's actually generally much quicker to draw or to maintain drawings that are intelligent. It may be a little bit more time-consuming up front to set up your drawings, just because you're going to be inserting a lot of information, especially if you're going to be inserting all of your process information.
Okay, thank you, Matt. Is there anything you'd like to say in closing?
No, I thank everyone for attending. Yeah.
Okay, great. If anyone did have a question today that was not answered, please send it to producer@aiche.org, and I will forward it to Matt. So now on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Matthew Leos for this very informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this webinar or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.